We're back and we are going to focus this conversation on building the convolution structure in Simulink. Now that we've established our baseline MATLAB frequency plan, it's time to bring that convolution equation to life in Simulink. As you can see here, we're building this model using a series of gain and sum blocks. This structure directly mirrors the mathematical expression of discrete time convolution. What's powerful about Simulink is that it allows us to pull variables directly from the MATLAB workspace. That means the same data we defined earlier, like our input signal and impulse response, can be used right here in the blocks. Each value from the impulse response, the HN matrix, is inserted into a corresponding gain block. These present the values of Hn minus K. Our input signal is a repeated staircase waveform. Instead of manually typing the values in, we just use the input variable we defined in MATLAB directly in the Simulink model. When you connect everything together, this entire block structure becomes a physical realization of the mathematical convolution operation, exactly like we did with the CONV function earlier. This is a crucial step. By designing it visually and confirming it with real data, we're preparing this model for the next phase, automatic HDL code generation and hardware implementation on FPGA. This is where software meets hardware, and it all starts with understanding the signal flow at this level. All right, now let's run our Simulink model and compare the output to our original frequency plan from MATLAB. Wait a second. This doesn't look quite right. The values aren't matching the MATLAB output. So what's going on here? Let's think it through. We're using the same input signal, and we've assigned the same impulse response values to our gain blocks. So why are the results different? Well, this is a great example of a common misconception. Assuming the tool confirms correctness just because it runs. But here's the truth. The tool is only as accurate as your understanding of the underlying theory. Remember, convolution involves the input signal sliding across the impulse response. That takes time. It's not instantaneous. And importantly, the length of the output signal is almost always longer than the input signal. So how long should it be? Here's the rule of thumb. The number of output samples should equal the number of input samples plus the number of impulse response samples minus 1. If you haven't done convolution by hand several times, this might catch you off guard. That's why I strongly recommend doing it manually before jumping into tools like MATLAB or Simulink. Now, here's another thing you need to consider. The input signal we're using is a repeating staircase function. That means it's looping through the same values over and over. So what likely happened here is that we didn't send the correct number of input samples into the gain structure. And this leads to an incorrect output. The fix is actually pretty simple. You need to pad your input signal with enough zeros to match the expected number of output samples. This ensures that the entire input sequence has enough room to properly slide over the impulse response without being cut off. Once you add the right amount of zero padding to your input, you'll see your output align perfectly with the lab results like here. And this confirms that both your model and your understanding are sound. Please like, subscribe, and comment so that I know you're out there. Have a great rest of your day.